In this lesson, we will discuss the design of the various types of direct current, or DC generators and alternators, that are used to supply electrical power to aircraft systems. DC generators are identified by the way in which their field windings are supplied with current. The three types of field winding connections are known as series, shunt, and compound. We will look at each type in turn, beginning with the series wound field. In a DC generator, the magnetic field is produced by stationary electromagnets, consisting of field coils wound around the pole pieces of the field permanent magnet. An alternating voltage is induced in the rotating armature coils before being converted to DC by the rotating commutator. In a series-wound DC generator, the armature, the field coils, and the external circuit are all in series. For simplicity, we can show the electrical circuit like this. This means that the same current which flows through the armature and external circuit also flows through the field coils. Since the field current, which is also the load current, can be large, the required strength of magnetic flux is obtained with a relatively small number of turns in the field windings. With this configuration, the output or terminal voltage of the generator is very low if there is no connection to the external circuit, as there will be no current flowing in the field coil, and only a weak magnetic field will be produced by the residual magnetism in the pole pieces. Since the load current passes through the field coil, as a load is connected and it draws current from the generator, this current increases the field strength and generates more voltage in the armature winding. The output voltage will therefore increase as the load current increases. A point is reached where any further increase in load current does not result in greater voltage, because the magnetic field has reached the point where no more magnetic lines of force can be absorbed by the pole pieces. This is known as the field saturation point. The output or terminal voltage of a series-wound generator, then, varies with the applied load. Aircraft systems require a reasonably constant voltage, so the series-wound generator cannot be used. A shunt-wound DC generator has its field winding connected in parallel with the armature. The term shunt is often used in the electrical world to mean in parallel with. Diagrammatically, the electrical circuit will look like this. Unlike the series-wound generator, the current through the field coils of a shunt-wound generator is independent of the load current. The shunt field windings have a large number of turns, and therefore require a relatively small current to produce the necessary field flux. When a shunt generator is started, the residual magnetism in the field poles will induce an EMF in the armature. This will cause a current to flow in the field coil. This, in turn, will increase the field strength, leading to a greater induced EMF, further increasing the field current. In this way, the time taken for the terminal voltage to reach its rated value, that is, the maximum voltage at which the generator can continuously supply its rated load current, is very rapid. Because the field current is not affected by the load current over the normal operating range of no load to full load, the drop in terminal voltage as the load current increases is relatively small, due only to the voltage dropped because of the internal resistance of the armature coil. The terminal voltage of a shunt generator can be controlled at a particular value by placing a variable resistance in series with the shunt field coils. The value of this resistance can be changed to control the amount of current flowing in the field circuit, and thus the generator output voltage. A compound wound DC generator is a generator with both series and shunt field windings. There are two sets of field coils, one in series and one in parallel with the armature. The two coils are always mounted on common pole pieces. Compound wound generators are designed to overcome the small drop in terminal voltage which occurs in a shunt wound generator when the load is increased. This voltage drop is undesirable where loads requiring a constant voltage are being supplied. By adding the series field with a suitable number of windings, the strength of the total magnetic field is increased when the load current is increased. The voltage drop caused by the increased load current flowing through the resistance of the armature is therefore compensated for by the increased strength of the magnetic field, and it is possible to obtain an almost constant voltage output. A DC generator does not normally require an external electrical supply to the field on startup, as the residual magnetism which remains in the field pole pieces when the machine is static is sufficient to begin the generation process. These types of generator are known as self-exciting generators. Because of the residual magnetism, as soon as the generator is rotated, there will be a voltage produced. This voltage causes a current to flow in the field coil, which increases the strength of the magnetic field. This, in turn, causes the voltage and field current to increase further until the output voltage reaches its controlled value. We know that magnetism can be lost, destroyed, or reversed in a number of ways. The loss of residual magnetism in a self-excited DC generator will prevent any build-up in output voltage. This loss of residual magnetism can be overcome by momentarily passing a current through the field in the normal direction. This procedure is known as flashing the field. Some generators are designed with no residual magnetism. This type of generator requires the field to be flashed to start the generating process each time the generator is run. Aircraft using this type of generator have a button or switch to allow the procedure to be carried out from the cockpit. Commutator ripple is the term given to the fluctuation of the voltage output of a DC generator, as the voltage rises and falls during the rotation of the armature loop. By increasing the number of coils in the armature, or the number of field coils, or indeed both, the pulsating or ripple effect of the DC produced by a generator can be reduced. Here you can see a sectional view of a DC generator. You can see that there are a number of coils on the armature. Each coil needs a pair of commutator segments. When aircraft first began requiring electrical power in appreciable amounts, the only practical way of converting the AC produced by a generator into DC was by use of a commutator. But there are a number of problems with the use of a commutator. The heavy load-carrying windings must be on the rotating assembly. and because of the high current flowing, there is a lot of sparking between the commutator and brushes, causing the brushes to wear out quickly. The era of solid-state electronic components has led to the development of the high-current diode rectifier. This is a solid-state device with no moving parts. Its electrical symbol is shown here. When placed in an electrical circuit, the diode rectifier allows current to flow unrestricted in the direction of its arrowhead, but blocks flow in the other. This means that the commutator is no longer required, as the generator's output can be converted to DC externally to the generator. In most modern light aircraft, AC machines known as alternators have replaced DC generators as the source of electrical power. In an alternator, the functions of the rotating and stationary components are reversed compared to those on a DC generator. The magnet with its field windings is on the rotating assembly, or rotor, and the heavy armature windings are on the stationary assembly, or stator. The field current, which is much lower than the armature current, is fed onto the rotor through brushes and slip rings. The advantages of an alternator over a DC generator are that it can be of a much lighter weight for the same power output. It will produce a more stable output at low engine speed, and it does not suffer with the problems of a commutator, as it uses a rectifier to convert AC to DC. That is the end of the lesson. Here are the main points that you should take from it. The output or terminal voltage of a series wound generator varies with the applied load. The output voltage of a shunt wound generator reduces slightly as the load increases. The output voltage of a compound wound generator can be constant with a varying load. The output voltage of a generator is controlled by placing a variable resistance in series with the field coil. A DC generator has a rotating armature and a stationary field. An alternator has a stationary armature and a rotating field. The AC output of an alternator is converted to DC using diode rectifiers. The advantages of an alternator over a DC generator are that it can be of a much lighter weight for the same power output. It will produce a more stable output at low engine speed, and it does not suffer with the problems of a commutator, as it uses a rectifier to convert AC to DC.